Hey everyone, and welcome to this explainer. I am so thrilled you're joining me today because, well, we're going to unpack something truly fascinating. Today, we're diving deep into the invisible engineering shield that protects an electric vehicle's absolutely most expensive component, the battery, from extreme heat. You know, if you've ever wondered why some electric cars can literally drive through a blistering desert and ultra-fast charge without breaking a sweat, while others suddenly just throttle their power, well, you're in exactly the right place. We're going to explore the cutting-edge hardware and the predictive software that makes modern EVs so incredibly resilient. It's a fantastic opportunity to learn something new today that is going to completely change how you look at the cars on the road right now.
Okay, let's dive into this. Thermal management is the difference between a vehicle that lasts 200,000 miles and one that fails prematurely. I mean, the stakes here are incredibly high. The core challenge for automotive engineers today is that lithium-ion battery. These cells are super sensitive to their environment. If they operate outside their optimal temperature range, it can lead to accelerated degradation, permanent loss of capacity, and that dreaded throttled performance. So modern EVs aren't just built to merely endure the summer heat, they're meticulously engineered to actively manipulate it, ensuring longevity and consistent power.
So here's a quick look at our roadmap for today. We'll cover the EV thermal challenge, compare air versus liquid cooling, and explore the smart loop ecosystem. Then we'll look at why 800-volt architecture wins, how software acts as a shield, and finally, we'll translate the whole shebang into a highly practical, heat-resistant checklist for evaluating your next vehicle.
All right, Section 1, the EV Thermal Challenge. Now, absolutely no car is naturally immune to extreme heat. It's just chemistry and physics, right? But modern engineers build active protection mechanisms directly into the vehicle to prevent degradation and avoid throttling your performance.
Which brings us right to Section 2, air versus liquid cooling. This is where we investigate the fundamental engineering divide in how these battery packs actually shed that dangerous heat.
So looking at this, there's a really stark contrast in how EVs handle heat. On one side, we have passive air cooling. This is an older, kind of budget-friendly design that just uses ambient airflow or internal fans. The problem? Well, when the outside temp creeps above 35 degrees Celsius, this system becomes a major liability. The car just doesn't have an efficient medium to carry the heat away. So to prevent catastrophic cell damage, the software triggers a thermal protection mode. This severely limits charging speeds, a super frustrating phenomenon a lot of people call rapid gate. But on the flip side, we have active liquid cooling. This is the absolute gold standard for long journeys. It circulates a dedicated coolant through internal plates or pipes, maintaining a highly stable sweet spot for the battery, right between 20 and 45 degrees Celsius. This prevents localized hotspots, stops chemical degradation, and allows for predictable, ultra-fast charging because the system can just aggressively dump heat when it needs to.
Now, there is a major misconception out there that small city cars are inherently worse in the heat compared to, say, massive luxury SUVs. But heat resistance is entirely based on the cooling architecture, not the vehicle's size. While older entry-level models did use air cooling to save costs, modern city cars like the Fiat 500e and the Mini Cooper SE are engineered with full liquid cooling. They're perfectly capable of handling the heat just as well as high-end luxury sedans. Now, quick tip for you. If you do happen to own a slightly older entry-level city car, maybe produced between 2020 and 2023 without liquid cooling, try to avoid long journeys when it's over 34 degrees outside. And whatever you do, avoid charging in direct sunlight for more than an hour. Moving right along to Section 3, the smart loop ecosystem. As electric vehicle platforms have matured, engineers have completely evolved past using simple, isolated cooling pipes.
So the really crucial point here is that modern cars use an integrated thermal management module. Think of systems like Marelli's ITMM or Tesla's famous Octovalve. These aren't just pipes. They act like brilliant central traffic controllers that treat the battery, the motors, the power electronics, and even the passenger cabin as a single connected thermal ecosystem. And there are three main functions at play here. First, heat sharing. If the battery is too cold, the system can actually scavenge waste heat from the electric motor and use it to warm the battery up. Pretty cool, right? Second, heat expulsion. During summer extremes, it directs all that excess thermal energy toward the primary radiators to literally just dump it out of the car. And third, selective active cooling. Using electronic valves, it can prioritize cooling for a specific, highly stressed component, like the inverter, while actually reducing the energy load on the pumps. It is literally a masterclass in efficiency.
Okay, Section 4. Why 800-volt architecture wins. We're shifting focus from the mechanical loops to the electrical design itself, because the way the electrical architecture is built dictates exactly how much heat the car has to manage in the first place.
Now, what's really interesting about this slide is how it demystifies the science of internal heat.
To understand why heat is generated when you plug your car into a fast charger, we have to look at Joule's law. Don't worry, we are not going to get bogged down in heavy math. But the equation is power equals current squared times resistance. The key takeaway for us here is that power loss, which manifests entirely as internal heat, is proportional to the square of the current. So the heat isn't just coming from the hot summer sun. A massive amount of it is actually being generated internally by the electrical current itself.
And this is exactly why the auto industry is making such a massive shift. By doubling the standard electrical architecture from 400 volts up to 800 volts, which we're seeing in fantastic cars like the Porsche Taycan, Audi e-tron GT, and the Hyundai Ioniq 5, you can deliver the exact same amount of power but with only half the current. And remember Joule's law? Because heat generation is proportional to the square of the current, cutting the current in half drastically slashes the amount of heat generated. This engineering leap is exactly what allows these vehicles to charge at mind-blowing, ultra-fast speeds while remaining incredibly cool.
Let's transition to Section 5, Software as a Shield. Because modern thermal management isn't just about hardware and physics, it is a highly predictive software science. Picture this. You're driving on a hot day and you punch a high-speed fast charger into your car's GPS navigation. Well, the vehicle's software knows that a massive 250 kilowatt surge of energy is about to hit the battery, and it knows that is going to generate a ton of heat. Through a feature called battery preconditioning, the car anticipates this event. It proactively activates the liquid cooling system miles before you even arrive, intentionally lowering the battery's temperature. It acts as an invisible shield, ensuring that the second you plug in, the battery is at the exact optimal temperature to absorb maximum power without immediately overheating and throttling your charge.
And finally, Section 6, your heat-resistant checklist. We've covered a lot of high-level engineering concepts today, so let's synthesize all of it into an actionable evaluation tool for you.
If you're evaluating a new vehicle, especially if you live in a hot climate, definitely keep this checklist in mind. Under What to Prefer, liquid cooling is an absolute non-negotiable standard for longevity. You're also going to want to look for heat pumps, which signal a highly sophisticated, bidirectional thermal system. Prioritize 800-volt architectures if you plan on taking frequent long road trips and using ultra-fast chargers. And make sure the software features active preconditioning via the GPS. On the What to Avoid side, steer clear of air-cooled batteries or pre-2023 older entry-level platforms that lack integrated loops, particularly if you live in extreme climates that regularly exceed 35 degrees Celsius. And as a golden rule for those older systems, just avoid charging for more than an hour in the blazing summer sun. Try to travel at night or charge in the shade whenever you possibly can.
I want to explicitly thank all of you for joining me on this deep dive today. I really hope you've learned something genuinely new about the incredible, invisible systems working behind the scenes to outsmart the heat. As we wrap up, I want to leave you pondering this final provocative thought. As these electric vehicle platforms continue to evolve beyond 800 volts and software becomes even more predictive, will thermal management eventually become so perfect that battery degradation simply becomes a thing of the past? It's a fascinating future to look forward to. Thanks so much for learning with me today, and I'll see you in the next explainer.